Today's problem. Given a square grid where each cell holds a stack of cubes, find the total area of its 3 orthogonal shadows. Take a moment. What would you do? Let's start from the very beginning. The input is a two-dimensional array called grid. It has n rows and n columns, so it's always a square. Each entry grid, I, j, is a non-negative integer that tells you how many 1 by 1 by 1 cubes are stacked at that position. Imagine a table with little towers of blocks. The number in each cell is the height of that tower. The output is a single integer. The sum of the areas of 3 shadows cast by the whole structure when light shines from 3 perpendicular directions. The top shadow looks straight down. Every tower that has at least one block contributes a 1 by 1 square to the top view. So the top area is simply the count of cells with height greater than 0. The front shadow looks from the front of the grid. For each column, the tallest tower in that column determines how many squares are visible from the front, because shorter towers hide behind the tallest one. So the front area is the sum over all columns of the maximum height in that column. The side shadow looks from the side. For each row, the tallest tower in that row determines the side view. So the side area is the sum over all rows of the maximum height in that row. The final answer is top area plus front area plus side area. Let's walk through the example. A 2 by 2 grid with heights, 1, 2, 3, 4. Top view. All 4 cells have height greater than 0, so top area equals 4. Front view. Column 0 has heights 1 and 3, max is 3. Column 1 has heights 2 and 4, max is 4. Front area equals 3 plus 4 is equal to 7. Side view. Row 0 has heights 1 and 2, max is 2. Row 1 has heights 3 and 4, max is 4. Side area equals 2 plus 4 is equal to 6. Total equals 4 plus 7 plus 6 is equal to 17. Why is this non-trivial? At first glance you might think you need to simulate the 3D shape, but the problem reduces to simple row and column maxima. The constraints say n is at most 50 and each height is at most 50, so in big O of n squared, quadratic time solution is easily fast enough. However, a naive approach that scans the grid 3 separate times does extra work we can avoid. The obvious thing to try is to compute each projection independently. First, count the top area by looping over every cell and incrementing a counter whenever the height is positive. That's one full pass over the grid. Second, compute the front area. For each column, loop over all rows to find the maximum height in that column. Then add that maximum to a running total. That's another full pass over the grid, but this time the outer loop is columns and the inner loop is rows. Third, compute the side area. For each row, loop over all columns to find the maximum height in that row, and accumulate those maxima. That's a third full pass. Each pass touches every cell once, so overall we do 3 times n squared operations. The time complexity is still big O of n squared, quadratic time because constant factors are dropped, but we are doing 3 separate traversals. The space complexity is big O of 1, constant time because we only keep a few integer variables, no extra arrays. The redundancy is clear. While scanning for column maxima we revisit the same cells we already visited for row maxima, and for the top count. We're essentially reading the grid 3 times when we could gather all needed information in a single read. This is the classic brute force, correct but not efficient in practice. The key insight. We can compute the top count, the maximum of each row, and the maximum of each column all in one single traversal of the grid. Think of it like a single walk through a warehouse where you simultaneously note which shelves have any boxes, the tallest stack in each aisle, and the tallest stack in each row of shelves. To do this we create 2 helper arrays of length n. One called rowmax to store the highest tower seen so far in each row, and another called callmax for each column. We also keep a simple integer top for the top area. Then we loop over every cell exactly once. For each cell at row I, column j with height h. If h is greater than 0 we increment top. Then we compare h with rowmax, I. If h is larger we update rowmax, I to h. Similarly we compare h with callmax, j, and update callmax, j if needed. After the loop finishes, rowmax holds the maximum height for every row. Callmax holds the maximum for every column, and top holds the count of non-zero cells. The final answer is top plus the sum of all values in rowmax plus the sum of all values in callmax. This uses big O of n extra space for the 2 arrays, but reduces the number of grid reads from 3 passes to 1. Let's break down each line conceptually. We declare the size n, we allocate rowmax and callmax filled with zeros, we set top to 0. The nested loops visit each cell. Inside we read the height, update top if needed, and update the 2 max arrays. Finally we sum top, all rowmax entries and all callmax entries. Every variable has a clear purpose and no step is wasted. Now let's trace the optimal algorithm on the example grid. 1, 2, 3, 4. We'll keep track of every variable at each step. Initially n equals 2. Rowmax is an array of 2 zeros. 0, 0. Callmax is also 0, 0. Top equals 0. We enter the outer loop with I equals 0. Inner loop j equals 0. Height h equals grid 0, 0 equals 1. Since h greater than 0, top becomes 1. Compare h with rowmax 0, 0, 1 greater than 0, so rowmax 0 becomes 1. Compare h with callmax 0, 0, 1 greater than 0, so callmax 0 becomes 1. Current state. Top equals 1, row max sad face 1, 0. Call max sad face 1, 0. Next inner iteration j equals 1. H equals grid 0, 1 equals 2. H greater than 0, so top becomes 2. Compare H with row max 0, 1, 2 greater than 1. So row max 0 becomes 2. Compare H with call max 1, 0, 2 greater than 0. So call max 1 becomes 2. State. Top equals 2, row max sad face 2, 0. Call max sad face 1, 2. Outer loop increments I to 1. Inner loop j equals 0. H equals grid 1, 0 equals 3. H greater than 0, so top becomes 3. Compare H with row max 1, 0, 3 greater than 0. So row max 1 becomes 3. Compare H with call max 0, 1, 3 greater than 1. So call max 0 becomes 3. State. Top equals 3, row max sad face 2, 3. Call max sad face 3, 2. Inner loop j equals 1. H equals grid 1, 1 equals 4. H greater than 0, so top becomes 4. Compare H with row max 1, 3, 4 greater than 3. So row max 1 becomes 4. Compare H with call max 1, 2, 4 greater than 2. So call max 1 becomes 4. State after loops. Top equals 4, row max sad face 2, 4. Call max sad face 3, 4. Now we compute the sum. Start with sum equals top equals 4. Add row max 0 equals 2 lambda operator. Fat arrow sum equals 6. Add row max 1 equals 4 lambda operator. Fat arrow sum equals 10. Add call max 0 equals 3 lambda operator. Fat arrow sum equals 13. Add call max 1 equals 4 lambda operator. Fat arrow sum equals 17. The algorithm returns 17. And there's our final result, 17, which matches the expected total projection area for the example grid. You'll spot this pattern when a problem gives you a grid of heights and asks for the sum of top, front, and side views, or any time you need row and column maxima together with a simple cell count. Time complexity is big O of n squared, quadratic time because we visit each cell once. Space complexity is big O of n for the two helper arrays. Try the next problem, same pattern. Subscribe for more beginner DSA walkthroughs.